The West Sea in January operates under a sky that has given up on light. At 7 in the morning, the sun is technically above the horizon to the southeast, but the overcast layer that sits at 800 meters absorbs what it offers and leaves the surface in the kind of gray that is less a color than an absence. Everything visible, nothing distinct. The horizon, a suggestion, and the North Korean coast to the north, a darker suggestion of what the gray is against. Water temperature at the surface is 2 degrees Celsius. The wind from the northwest is 14 knots and consistent. USS Mason makes 17 knots on a northwesterly heading, 47 nautical miles south of the northern limit line. Operating in support of a combined USROK readiness demonstration that the two commands have been conducting for 6 days. She is not at general quarters. She is at modified readiness, the intermediate posture between full GQ and routine watch standing, with the gun mount manned and the Aegis in active scan, but the crew otherwise in the transition between morning watch and the day routine. It is 7:09 a.m. when the shore battery fires. The 130-millimeter coastal artillery battery position on the North Korean coast north of the NLL is a fixed installation that the intelligence community has known about for a long time and has assessed as operational but rarely active in a fire mode against U.S. surface combatants. The assessment has been based on historical restraint. At 7:09 a.m., the battery fires a 6-round salvo at the Mason's last radar-fixed position using a fire control solution that was generated from the DPRK's coastal radar network over the past 14 minutes. The 130-millimeter projectile weighs approximately 33 kilograms and travels at approximately 900 meters per second. At the range the battery is engaging from, the time of flight is approximately 22 seconds per round. 6 rounds in a salvo, fired at 1-second intervals, takes approximately 28 seconds to complete. The Mason's SPY-1D detects the muzzle flash from the battery's first round and classifies it correctly. Shore-based direct fire, bearing 347, at 7:09:04 a.m., 3 seconds into the time of flight of the first round. The general alarm sounds at 7:09 and 7 seconds a.m. The helmsman puts the wheel over to change course. The standard incoming fire maneuver is to present the stern to the firing bearing, reducing the ship's profile from a broadside to a narrow stern aspect. The ship's turn begins at 7:09 and 8 seconds a.m. At 17 knots, the time required to complete a 60-degree course change is approximately 25 seconds. The time of flight of the first round is approximately 22 seconds. The first round is a miss. It lands in the water approximately 180 meters off the Mason's port beam, having been aimed at the ship's pre-maneuver position. The second round is also a miss, further off due to the ship's turn. The third round misses. The fourth round misses. The fifth round strikes the ship. It hits the port side of the Mason superstructure at the 02 deck level, between frames 44 and 48, at approximately Mach 0.6. The projectile has been decelerating through its flight path and has lost significant velocity by the time it reaches the target range. At Mach 0.6, a 33-kilogram steel projectile is not moving slowly. It punches through the 6-millimeter aluminum superstructure cladding, the 12-millimeter steel structural frame at frame 46, and detonates its base fuse delay charge approximately 0.8 meters inside the superstructure. The detonation produces a fragmentation pattern primarily to the sides and aft of the detonation point, with the forward-facing side of the burst contained by the structural steel of frame 46. The detonation occurs inside the ventilation trunk. The Mason's main ventilation system, the network of sheet metal ducts that distributes conditioned air throughout the ship, runs its primary port side trunk through the 02 deck level superstructure in the frame 44 to 48 zone. This is a major arterial duct, approximately 60 centimeters by 80 centimeters in cross-section, that feeds the port side distribution network for the aft engineering spaces. the aft crew berthing, and the after damage control lockers. The duct is not structural. It is 1.6 millimeters galvanized steel sheet formed into a rectangular section and supported by mounting brackets at every frame. When the 130 millimeter projectile detonates inside the duct, the fragmentation tears the duct apart at the detonation point and severely damages the adjacent duct sections for approximately 2.4 meters forward and aft. The duct runs directly adjacent to two ventilation damper assemblies, the automatic fire dampers that are designed to close in the event of a fire or emergency to isolate one section of the ventilation system from another and prevent fire and smoke from propagating through the duct network. Both fire dampers are disabled by the fragmentation. The motor actuators that drive them are torn from their mounts. The damper blades themselves, spring-loaded fusible link devices that normally snap shut when the fusible link melts at 74 degrees Celsius, are physically severed from their pivot mounts. The duct is open. The dampers are gone. The ventilation system continues operating because the supply fans are running, and the emergency shutdown command has not yet been given. The sixth round is a miss. The shore battery falls silent. The engagement has lasted 28 seconds. In those 28 seconds, the Mason has taken one hit from a 130 millimeter coastal artillery round. The hit is survivable. The ship has not lost propulsion. No major systems have been disabled. There is no flooding, and the detonation was in a non-critical space. But the detonation has started a fire. The fragmentation pattern from the 130 millimeter round's detonation inside the ventilation duct has produced approximately 200 secondary fragments, traveling at velocities between 200 and 900 meters per second, distributed through the duct interior and through the duct walls into the adjacent superstructure spaces. One fragment cluster has punctured the insulation on a 440-volt electrical cable bundle that runs in the cable tray, adjacent to the duct at frame 46. The insulation punctures have exposed the cable conductors. Another fragment cluster has punched through the duct wall into the space on the starboard side of the trunk, a utility space containing the aft engineering electrical panel junction box, and has ruptured a hydraulic fluid line that serves the aft stabilizer fin system. The hydraulic fluid, spraying from the rupture at 2,200 pounds per square inch, contacts the exposed electrical conductors in the cable tray. An arc forms. The hydraulic fluid ignites at 7:09:39 a.m., 11 seconds after the 130 millimeter round detonated. The fire is small at its origin. A hydraulic fluid spray fire where the fluid mist is contacting the arc and burning as it exits the ruptured line. But the fire is in a space that is directly connected to the ventilation duct through the fragment holes in the duct wall. And the ventilation duct is the ship's main port-side air circulation trunk, which is currently operating. The supply fan is still running because the emergency shutdown command requires a manual input from DC Central, and DC Central has been receiving damage reports for approximately 8 seconds and has not yet processed the fire. The ventilation system is actively drawing air through the fire space, picking up heat and combustion products, and distributing them through the duct network to the aft engineering spaces, the aft crew berthing, and the aft damage control lockers. The duct is not circulating smoke yet. The fire is too small to produce significant smoke at this stage. But it is circulating warm, hydrocarbon-laden air from the burning hydraulic fluid into spaces occupied by crew members at their modified readiness stations. And the fire is growing because the ventilation system is supplying it with fresh, oxygenated air at the rate of approximately 800 cubic feet per minute through the connected duct network. At 7:09:47 a.m. DC Central receives the fire alarm for the 02 deck, frame 44 to 48 space. At 7:09:52 a.m., the watch officer in DC Central gives the order to shut down the port-side ventilation system. The supply fan stops. The duct falls to ambient pressure. The fire in the utility space continues burning, but it is no longer being actively fed by the ventilation system. At 7:09:57 a.m., the chief engineer arrives in DC Central. He has been in the engineering spaces when the general alarm sounded and has moved toward DC Central immediately. He reads the damage board in 8 seconds. 130 millimeters hit at frame 46. Port side, 02 deck. Fire alarm active 02 deck frame 44 to 48. Port ventilation system secured. No flooding, no propulsion loss, no power loss. He pulls the ventilation system schematic from the engineering drawings rack on the DC Central bulkhead. A set of laminated drawings that show the complete ventilation duct layout for the ship. And looks at the frame 44 to 48 zone. He sees the problem immediately. The fire dampers at frame 46 are on the drawing as installed components. The 2 automatic fire dampers that should have closed when the fire alarm activated. Every other fire alarm on the ship triggers automatic damper closure. These 2 did not close because they cannot close. They have been disabled by the fragmentation. The drawing shows them as present. The ship's fire damper status panel in DC Central shows them as failed. A red light for each damper position, indicating that the closed position confirmation signal is not being received. 2 failed fire dampers in the port side main ventilation trunk at frame 46. This means that even with the supply fan secured, the duct is open between the fire space and the aft duct network. Natural convection, hot air rising through the open duct from the fire space, will continue to push heated air and combustion products through the duct toward the aft spaces, not at the rate of the powered supply fan, but continuously and in proportion to the fire's heat output, which is increasing as the hydraulic fluid fire grows. At 7:10:09 a.m., the chief engineer calls the DC team at the frame 46 space. What is the status of the fire? The repair party leader responds. Fire is active in the utility space, starboard side of the vent trunk. Hydraulic fluid looks like a pressurized line has ruptured. AFFF team is at the door. We need to know about the dampers before we go in. If the duct is open, AFFF application will push smoke back through the duct to the aft spaces. This is the second layer of the problem. AFFF foam works by blanketing the fuel surface and cutting off the oxygen supply to the fire. But AFFF application in a space connected to an open duct creates a pressure differential. The foam application changes the air pressure in the space slightly. And the open duct connection means that pressure change propagates through the duct network. In a small space with a large open duct connection, AFFF application will push the combustion products through the duct rather than containing them. The aft spaces, which have crew members in them at their damage control stations, will receive the displaced smoke and combustion gases. He cannot use AFFF with the duct open. The duct fire dampers are disabled. The dampers cannot be replaced at sea. He needs to isolate the duct mechanically, physically block the duct at a point that separates the fire space from the rest of the duct network, before any fire suppression in the space can be safely executed. There are 2 physical access points to the ventilation duct in the frame 44 to 48 zone. The clean-out access panel at frame 44, which allows entry into the duct from the port passageway side, and the inspection panel at frame 48, which allows access from the starboard side. Both are on the drawing. Both are approximately 40 centimeters by 50 centimeters. Large enough for a person to reach into with arms and torso, but not large enough to climb through. The solution assembles in his mind in approximately 20 seconds. He needs to install temporary physical blocks at both the forward and aft sides of the damaged duct section, blocking the duct passage between the fire zone and the rest of the duct network. The blocks do not need to be airtight. They need to be good enough to prevent the convective flow through the duct while the fire is being fought, and good enough to prevent AFFF from propagating backward through the duct to the aft spaces. A sheet metal plate, a wooden plug of adequate size, or even a folded fire blanket pushed into the duct at each access point will disrupt the convective flow sufficiently. He calls the DC team. I need 2 people at the frame 44 duct access panel and 2 people at the frame 48 duct access panel. The objective is to install a physical block in the duct at each location. Sheet metal from the DC kit, folded fire blanket, anything that will interrupt airflow in the duct. You need to reach into the access panel and push the material into the duct cross-section until it blocks the passage. Do not enter the utility fire space until I confirm that both blocks are in place. I need the blocks installed in 4 minutes. He then calls the hydraulic system watch. Identify the hydraulic supply circuit to the aft stabilizer fin system and isolate it at the upstream valve. The rupture in the utility space at frame 46 is in the stabilizer hydraulic line. If you isolate the upstream valve, the fuel supply to the fire will drop to whatever is trapped in the line, maybe 4 to 6 liters. The fire will run on that and then decrease significantly. The hydraulic isolation valve for the aft stabilizer fin system is at frame 42 in the port machinery space passageway, accessible from the ship's main internal passageway without going through the fire space. The machinist's mate on watch reaches it at 7:10:51 a.m. The valve is a 3/4-inch ball valve with a lever handle. He turns it to the closed position. The hydraulic pressure to the rupture point drops to 0 within approximately 8 seconds as the trapped fluid in the line pressurizes to the rupture point and stops flowing. The rate of hydraulic fluid spraying from the rupture drops immediately. The fire does not go out. The residual hydraulic fluid that has already escaped from the ruptured line and soaked into the utility space surfaces is still burning, but the continuous fuel supply is gone. The fire is now running on residual fuel rather than a pressurized spray. At the frame 44 duct access panel, the first DC team has opened the panel and is working the temporary block installation. The panel reveals the interior of the main port side ventilation duct, a 60 by 80 centimeter rectangular passage of galvanized sheet metal running forward and aft, with the frame 46 damage visible approximately 1.2 meters aft of the access point as a ragged opening in the duct wall where the fragmentation tore through. The DC team member reaches into the duct with a folded fire blanket, a woven fiberglass material rated to 550 degrees Celsius, and pushes it into the duct cross-section until it fills the passage forward of the damage. The fire blanket is not an airtight seal, but pushed firmly into the 60 by 80 duct opening, folded to approximately 45 by 70 centimeters. It blocks the convective airflow adequately. He holds it in place with one hand, while his partner uses a length of duct tape from the DC kit to secure the blanket edges to the duct interior walls. The tape does not seal the blanket. It anchors it. Forward block installed at 7:11:43 a.m. At the frame 48 duct access panel, the second DC team is working the aft block. The frame 48 panel is on the starboard side of the duct trunk. The same duct, a different access point 2 frames aft of the fire zone. The approach is the same. Folded fire blanket, pushed into the duct cross-section, taped to anchor it. The complication at the frame 48 position is that the duct interior at this point is warm. Not dangerously so, but enough to make the hands uncomfortable when reaching in. The duct has been receiving heated air from the fire space for approximately 2 minutes before the supply fan was secured, and the metal of the duct wall is still holding some of that heat. The team member reaches in and pushes the blanket into position. The warmth through the fire blanket's protective layer is felt as a mild discomfort, not a hazard. Aft block installed at 7:11:59 a.m., 16 seconds after the forward block. The chief engineer receives both confirmations at 7:12 and 4 seconds a.m. He calls the AFFF team at the utility space door. Both duct blocks are in place. You have authorization to enter the space and apply AFFF. The fire is running on residual fuel only. The hydraulic supply has been isolated. Application should achieve suppression. Watch for reflash. Do not open the duct access panels again until I authorize. The AFFF team enters the utility space at 7:12:09 a.m. in full SCBA gear with a 1.5-inch AFFF line. The space is approximately 2 meters by 3 meters, and the fire, now running on residual hydraulic fluid rather than a pressurized spray, is producing less intense flame but still burning along the surfaces where fluid has soaked in. The AFFF is applied to the fire face in a sweeping pattern from the doorway. The first application knocks the visible flame. A second application 30 seconds later confirms no reflash on the primary surface. The team enters the space and traces the duct wall fragments, locating a secondary flame point where a fragment has embedded itself in the cable tray insulation and is smoldering. Water from the backup hose line extinguishes the secondary point. The fire in the utility space at frame 46 is confirmed out at 7:13:44 a.m., 4 minutes and 5 seconds after the round detonated. The post-fire assessment begins at 7:15 a.m., when the space temperature has dropped sufficiently for a full entry without SCBA. The damage picture is specific. The ventilation duct at frame 46 is ruptured across approximately 2.4 meters of its length and will require replacement at the next yard period. The 2 fire damper assemblies are disabled and will also require yard replacement. The hydraulic line rupture at the aft stabilizer fin circuit is confirmed as a clean shear fracture at the line's bracket attachment point. The stabilizer fin system is offline with the hydraulic supply isolated. The ship will complete its transit without active stabilizer fin control, relying on passive stabilization. In the current sea state, this means slightly more roll than normal, but not a safety concern. The 440-volt cable bundle that was punctured by fragmentation and caused the arc is assessed by the electronics technician. 4 cables in the bundle have damaged insulation, 2 of which have actual conductor exposure. The damaged cables are isolated at both ends, and temporary jumper connections are run from the junction box using the backup cable runs that the ship's electrical design provides for exactly this contingency. The aft engineering electrical panel resumes normal operation at 7:28 a.m. The 2 duct blocks, the fire blankets taped into the duct at frames 44 and 48, remain in place as permanent measures until the duct can be repaired at the yard. The ventilation to the aft spaces is rerouted through the starboard side trunk only, at reduced capacity, using the cross-connect dampers in the ventilation control system. The aft spaces operate at reduced ventilation, warmer than normal but habitable. The most significant lasting consequence of the engagement is the loss of the 2 fire dampers in the port side trunk. Without fire dampers at frame 46, any future fire alarm in the frame 44 to 48 zone will not receive automatic damper isolation. The Fire Watch team posts a dedicated lookout at the frame 44 and frame 48 duct access points for the remainder of the transit, prepared to install fresh fire blanket blocks immediately if a fire alarm sounds in the zone. At the post-event debrief at Busan, the chief engineer was asked 2 questions. The first was whether the temporary duct block solution, fire blankets taped into the duct, was in any technical manual. He said no. He said the principle was in the ventilation isolation section of the damage control reference manual. But the specific application of fire blankets as duct blocking material was not documented. He said he looked at the drawing, understood what the duct needed, and used what was available in the DC kit. The second question was whether he had known, before this event, that the fire dampers at frame 46 were in the ventilation trunk at that location. He said he had not specifically known which frames contained the dampers. He said he found them on the drawing. He was asked how long it took him to find them on the drawing. He said approximately 3 seconds, because the damper symbols on the ventilation schematic are standardized and visible at the scale the drawing was printed. He said the drawing had been in the DC Central drawing rack since the ship was commissioned, and he had read it before, as part of his familiarization with the ship's systems. He said the drawings are there for exactly this moment, not to be consulted after the fact. but to be known well enough that when you need to consult them quickly, you know where to look and what you are looking for. One 130mm coastal artillery round detonated inside the port side ventilation trunk at frame 4602 deck. 2 automatic fire dampers physically disabled by fragmentation, preventing automatic duct isolation. Hydraulic fluid line rupture in adjacent utility space from secondary fragmentation. Arc formation from cable bundle puncture, igniting hydraulic fluid spray. Fire began at 7:09:39 a.m. Port side ventilation system manually secured at 7:09:52 a.m. Hydraulic supply to rupture point isolated at 7:10:51 a.m. Temporary forward duct block installed at 7:11:43 a.m. Temporary aft duct block installed at 7:11:59 a.m. AFFF application authorized at 7:12:04 a.m. Fire confirmed out at 7:13:44 a.m. 4 minutes and 5 seconds from ignition. Aft stabilizer fin system offline. Aft ventilation rerouted via starboard trunk at reduced capacity. Electrical panel restored at 7:28 a.m. Ship status operational. The ventilation schematic that the chief engineer used at 7:09:57 a.m. The laminated drawing that showed him the fire damper locations at frame 46 in approximately 3 seconds remained on the DC Central workstation for the remainder of the transit, unrolled and positioned so the frame 44 to 48 zone was visible without unfolding. It was rolled and returned to the drawing rack when the ship entered Busan Harbor. The drawing was not annotated. It did not need to be. It was exactly as printed, exactly as accurate as the day it was commissioned. And it showed exactly what it needed to show. It showed where the dampers were. It showed where the access panels were. It showed how the duct connected to the aft network. Everything that was needed to build the solution was on that drawing. The solution itself was assembled from what the ship carried: fire blankets, duct tape, a hydraulic isolation valve, an AFFF line, by people who understood what the problem was and what the pieces were for. The drawing was 4 feet by 3 feet and weighed approximately 200 grams. For 4 minutes and 5 seconds on a January morning in the West Sea, it was the most important document on the ship.